Hello and welcome everyone. My name is Hannah Mason. I'm a technical editor at Composites World. I want to thank you for joining us today for this webinar titled Strain Measurement Solutions for Composite Testing, brought to you by Composites World and presented by Instron. In this webinar, Instron will discuss the different solutions for strain measurement on composite materials, such as strain gauges, clip-on extensometers, video extensometers, and digital image correlation, or DIC. Our presenters will discuss the advantages and disadvantages of each and when you might prefer one method over another. So we've got two presenters today, as you can see on the screen here. The first is Stefan Botsky, Senior Applications Engineer at Instron. Stefan has a background in mechanics and data analysis. In his current role, his primary focus is on static high-force testing for composites and other high-strength material applications. He is also a voting member and recording secretary for the ASTM D30 committee focused on composite materials. Joining him, we also have Ashley Davis, applications engineer. Ashley is a mechanical engineer with a diverse background, including work in quality, automation, business development, and now applications engineering. Like Stefan, in her current role, her primary focus is on high-force testing, static high-force testing for composites and other high-strength material applications. So their presentation will be followed by a question and answer session at the end. So attendees, if you have a question, you can type it in at any time during the webinar in the Q&A tab that you see at the right of your screen. Next to the Q&A tab, you'll also see tabs for polls, which will come up. Our presenters will bring up some polls during the presentation, so you'll go there for that. And a handouts tab, which has several resources available for download at any time during the presentation. The webinar is also being recorded, and when complete, will be made available to you via email from Composites World later. So without further ado, I'll hand it over to our presenters. Welcome, Stefan and Ashley. Take it away.
Thank you. Thanks for the introduction, and thank you everybody for joining our webinar today. First, I'd like to go over the agenda today. The agenda is pretty short, but the presentation is pretty packed, so we'll see how far we're getting with questions today. But first, we want to talk about the composite materials and properties for anybody who's not that familiar with that yet, with the challenges that these materials are giving us in terms of testing. Then we're going to look at the strain measurement techniques that are being used for composite testing. And then in the third section of our presentation, we want to show you some actual examples where we tested composite materials and used various strain measurement techniques, all the ones that we're presenting on today, to give you some hands-on examples. And then if we have enough time at the end, we'll want to open it up for questions for you. At this point of the presentation, I'd like to do a quick poll on what people are actually using right now for their strain measurement techniques, like in your lab. What are you using? So I am not able to see the poll, so Hannah, if you can let me know when the poll is over, then I'll continue with the presentation.
Yeah, so it looks like it's open. Got some responses coming in. I don't know, Ashley, are you able to see the poll results on your screen too?
Yeah, so Stefan, it looks like we have about 44% use bonded strain gauges, 33% use clip-ons, and 22% use video extensometry. Then I don't have anything for lasers.
Okay, all right, very good. Yeah, no surprises there. Thank you everybody for letting us know. It's always very interesting to see what people actually use in their labs. So we're going to go over composite materials real quick here. What does it actually mean? So it means that you have two or more distinct phases. So you usually have a matrix material and then you have a reinforcement. So it's a combination of two materials, or at least could be the same material in distinct phases. So for matrix materials, common materials used there are polymatrix composites, so it's like a polymer matrix, or you could use ceramics, metals, and then there's also many examples in nature, like wood would be a natural occurring composite. Common reinforcements could be discontinuous fibers. So you see a couple examples over here for that, like short fibers or just particles. Or you could have continuous fibers. And these fibers, which you see here on this side, different orientations of the fibers all the way through. And these could be made out of all kinds of different materials, carbon fiber, for example, glass fiber, basalt. And nowadays you also see a lot of natural fibers being introduced, people trying to make composites out of natural fibers like hemp or bamboo. I've seen there's all kinds of examples, and also kind of a trend towards natural resins to be used. Today we'll focus on polymer matrix composites reinforced with carbon fiber. Now, traditional materials like metals or plastics are considered isotropic, which means that their properties are independent of the direction. So, for example, if this was a piece of steel and you would apply a load, it wouldn't really matter at what point you apply the load. It would be more or less the same. It would have the same strength. Composites, on the other hand, are considered anisotropic, which means that the bulk properties vary strongly with the direction that a load is applied. So if we take this example down here, and you see these black dots and you see these lines go through, so they're all supposed to be those reinforcements we saw on the previous slide, all oriented towards direction number 1. So if you were to apply a tension or compression load in direction number 1, the material would be very, very strong, because all of these fibers are there to take up that load and make the material really strong and take up that load. In direction number 2 and 3, though, there's really only the matrix and then the adhesion between all of the matrix and fiber materials that would act against that load. So it's going to be much, much weaker in direction number 2 or 3 if truly all fibers are oriented only in direction number 1. Now there's of course all kinds of mixes out there, and usually people would use a more balanced material, but still there's all kinds of things for you that you need to determine to fully know the properties of your material. So for example, you would need to check the tensile strength of your material, as well as the moduli of your tensile of your material in the tensile direction here in all 3 directions. So in direction number 1, 2, and 3, you need to test that material to fully determine the tensile strength and moduli. The same is true with compression, because composite materials are usually much weaker in compression than they are in tensile. So you need to do all those testings also in compression, which usually involves a lot of fixed string. The same is true then with shear. So you need to determine all the different combinations in shear, and then as well for the Poisson's ratio, which we'll touch on a little bit later. Another thing to keep in mind is that you need to simulate also the condition that your material will be used in. So composite materials take up moisture usually, so you need to simulate that. You need to condition your materials until they're fully saturated, just like they would be in their end application. And then you also need to think about temperature that your material needs to operate at. So you need to simulate that, which is traditionally done or usually done with an environmental chamber on your testing machine. And we'll also show you a few examples of that later. Now, to show you some of those examples, some of those challenges really when testing these materials, we would like to show you a video that demonstrates some of those challenges. There's certainly a lot of them, and that we're facing when we're testing carbon fiber reinforced plastics. So this is in this video recorded at 10,000 frames per second. We have a carbon fiber specimen, which is very, very stiff compared to traditional materials, and you can see that it's even recorded at 10,000 frames per second. The break really happens instantaneous, and the whole material really kind of explodes on you. For this test, the measurements, the strain measurements, were taken in the actual direction of the coupon, of the loading axis, and it was taken with a video extensometer on the front and with a clip-on extensometer on the back. And the video extensometer, which is our advanced video extensometer, the AV2, measured the strain on the flat side here, and then on the opposite side we used the clip-on extensometer. Okay, so in this next part, Ashley will kick it off with some strain measurement techniques that are traditionally used for composites testing.
Great, thank you, Stefan. So to kick things off, let's talk about some typical strain measurement considerations, such as what Stefan showed, just reiterating. Extensometers need to be able to survive at explosive failures if strain at failure is required for your testing. And then most importantly, the strain measurement solutions that need to be able to meet the requirements of the appropriate strain measurement standards. So requiring that high accuracy and resolution to ASTM E83 classes B1 or 2, or ISO 9513 class 1/ISO 527-1 Annex C. And the graphic that we're showing here is showing the different ASTM and ISO classes from least strict on accuracy on the bottom to most strict. Generally, we need to operate at temperatures from -80 to 200 degrees Celsius. Chamber units can typically provide these low temperature or high temperature testing environments. The picture on the left is actually showing a compression after impact fixture that's been piggybacked between some wedge grips inside of a chamber. So the specimen and the fixture are going to be subjected to an extreme temperature and then compressed until failure. The picture on the right shows somewhat of an extreme visual example of low temperature testing, but it's just showing that not only is the environment going to affect your specimen, but also your grips. So your grips and fixtures also need to be able to handle any kind of temperature changes. If you require Poisson's ratio or shear strain, we're going to need biaxial strain measurements, meaning longitudinal and axial and lateral or transverse. Just as a reminder that Poisson's ratio is the ratio of expansion along one axis to contraction along the opposite axis when a material is subjected to tensile or compressive forces. So this is negative transverse strain over axial strain. And showing on the right is just an example of one of these contacting clip-on extensometers that can handle both longitudinal and lateral strain at the same time. So keeping these situations in mind, the types of solutions that we're going to cover today are contacting extensometers, non-contacting extensometers like our AVE2, as well as bonded strain gauges. So kicking it off, high level for contacting extensometers, manual axial clip-ons are available in a variety of gauge lengths and strain rates. They're typically considered as rugged and lightweight and are able to handle most high shock breaks. We show an example of one remaining on in our lab. They are accurate to 0.5% of the gauge length, so your accuracy is dependent on what gauge length you're testing to. They can be used inside of chambers for hot and cold temperature testing. And then they are capable of measuring axial strain, transverse strain, or both. But depending on the type of strain measurements that you want to take, your part numbers are going to vary. It's not going to be a one-size-fits-all. Next, for non-contacting video extensometers, the Advanced Video Extensometer, or AVE2, is able to provide high accuracy strain measurements, meeting composite standards including ISO 527-4-5. It has a patented LED lighting and fan system, which prevents environmental influences. It doesn't require the operator to attach the extensometer, but it does require some specimen preparation and strain markings on the specimen for the video. It can be used on chambers for cold and hot tensile testing by actually attaching to the outside of the chamber. And then it can also be used for full field strain measurement using that digital image correlation software, or DIC. And I'm going to let Stefan talk about that next.
Thank you, Ashley. So digital image correlation, that is an optical technique, and it really compares the images of a tested specimen's surface to generate a full field strain and displacement map. So this enables you to analyze advanced strain characteristics, by visualizing the strain and the displacement over the full two-dimensional surface of your specimen, like you can see here. And that is being done with a random speckle pattern, and the camera then So when you load your specimen, the video extensometer will record the images during the test, and it's an adjustable rate, which you can set how many pictures to take per second. And the DIC software will then compare the images to each other and visualize the strain field for you. So you can now add a digital extensometer, for example, or a digital strain gauge to your specimen. And we'll go over some interesting examples for this in the later part of the presentation. Strain gauges, which I'm not too surprised that most of you are using those because they are required in many instances. So strain gauges are very common in composite testing specifically. I don't see that really being used in too many other material applications. And we covered some of those reasons earlier already. But yeah, in some cases, there's really no other solution available because either the testing standard requires it, or because of the testing fixture that you need to use, for example, in compression testing of your composite materials, won't allow you to use of a traditional clip-on extensometer. There simply won't be enough space. Strain gauges themselves need to be used with the appropriate condition electronics in order to process the resistance change and then take that to calculate your resulting strain. It's pretty common to use multiple strain gauges at once, and those readings are typically combined, and then you can generate things like the average actual strain or width strain of your test. You can do the differences in the actual strain to determine the bending that is going on during your testing, and that is a very important part, especially for compression testing, because you don't want any kind of bending or buckling going on. And then you can also use multiple strain gauges to determine shear strains, for example. One example for that, so the biaxial strain measurement, which is the relation between the actual and the transverse strain, is often required in composite testing standards to determine the Poisson's ratio, like we covered before, and also the shear strains of your material. So a good example for that is a V-notch shear test, as it is described in the ASTM D5379 testing standard. That's a good example for a standard that requires you the determination of the shear properties of your material. This test method requires you to use at least 2 strain gauges centered in the gauge section of the specimen, which you can see here, so that V-notched section of your specimen. And these gauges need to be mounted at plus/minus 45 degrees to the loading axis. And the gauge section is a compromise based on the type of material that you're testing, because it can really influence which gauges you should use. And this testing standard actually has some recommendations on that, which are given in section 7.51. So that should help you to determine the right strain gauges for this kind of testing. And you can see kind of the fixture with the specimen in here. It would be loaded from the top. It's sitting on a compression platen, and then this anvil here would come down and initiate the load into the specimen. So for this one, really, there's only strain gauges you can use. The other option you could think about would be a full field DIC, which, this is obviously very localized with the strain gauges, and the DIC then kind of gives you the full field, and you can then later on go and apply the strain gauges in the areas that are most interesting to you.
So to summarize the 3 types that we just covered in a broad sense, for our axial clip-on, the AVE2, and our bonded strain gauges, in terms of ASTM ISO classification, our clip-on is guaranteed to meet ASTM Class B2 and ISO Class B1. The AVE2 is up to ASTM Class B1 and ISO Class 0.5. And I just have some asterisks because that classification is going to be dependent on the lens that you're testing which can affect your field of view and the gauge length that you've marked on your specimen. And then your bonded strain gauges, that's going to be variable and is going to come from the manufacturer of those bonded strain gauges. In terms of temperature range, that clip-on, as I said before, is capable of going inside of a chamber and can handle -100 to 200 degrees Celsius. The AVE2 is capable of viewing through the window on the outside of the chamber and can handle from -20 degrees to 350 degrees Celsius. I have a couple more asterisks because if we get any lower than negative 20 degrees Celsius, we risk actually frosting over the glass on our chamber, which can cause visibility issues with the AVE2. So you have to be cognizant of that. And then the strain gauges have the highest temperature range of negative 269 to 800 degrees Celsius. Your gauge length for your axial clip-ons, that's going to be fixed. So if you have varying gauge lengths, 10 millimeters, 20 millimeters, 50 millimeters, you have to purchase a clip-on for each one of those gauge lengths. Your AVE2 is variable as it is able to read the gauge length markings on the specimen for you. And then your bonded strain gauges are also going to be fixed gauge lengths, 3 millimeters, 6 millimeters, and you're going to have to purchase ones for the different gauges you want to test with. In terms of price, the clip-on is considered more affordable, lower in the price range. Your AVE2 is going to have a higher price point as it is automatic and able to read those variable gauge lengths. And we'll talk a little bit more about other features of the AVE. And your bonded strain gauges, we considered high because of the cost of having to have those actually installed onto the specimens themselves. And in terms of installation, clip-ons, while it is manual, it is very easy to install a clip-on. They're very repeatable. The AVE2 is extremely easy as it's already set up. Really, you just need to make sure that you're marking your specimens with the proper gauge length. So we consider this easy. And then bonded strain gauges, we consider this difficult as you might have to have the specimens sent to an outside vendor to be bonded or have an operator doing this process for you and making sure that they're properly adhered to the specimen before test. So with that, what we're going to do is we're going to show the examples of the testing that we did here at Instron. Just to say before we kick it off, in the next section, we're going to show you these examples that we mentioned earlier. It's important to understand that what we're showing is not going to be a substitute for reading the full testing standards that we cover. Also, the equipment that we used for the testing is not calibrated or verified within our lab because we are constantly changing fixtures and load cells. And the specimens that we use, CFRP, we're kind of at the mercy of what we have on hand. So some of them are leftovers from customers, but we do also have some that we were able to source from our partners like the University of Utah. So these specimens we have, they're not always going to be a perfect match for what we have on hand. So please just take this as an example for what a test could look like on your testing machine, but hopefully you're able to take some of the feedback or techniques back to your own lab and maybe learn something from what we're showing today. So the in-house testing that we did a 2-inch clip-on and the AVE2 to tensile test ASTM D3039. We also did a bonded strain gauge specimen in a combined loading compression fixture, or CLC, to ASTM D6641. So the following are the results for these 3 types of tests. For our tensile setup, the ASTM D3039, we used an Instron 6800 floor model 100 kilonewton frame, or 22,000 pounds, a 100 kilonewton load cell, 100 kilonewton hydraulic wedge grips, serrated jaw faces 57 millimeters high by 50 millimeters wide, specimen alignment stops, Blue Hill Universal software, and we used a test rate of 2 millimeters per minute, which is dictated by the standard. The specimens that we have on hand are polymer matrix composites. Again, we don't know exactly what they are, but they were all unique to one another. Our first specimen is a tabbed 15 by 2 millimeter, which had a matte finish on both sides. Our second specimen was untabbed 15 by 2 millimeter. It was a different material. The best way I could describe it is it felt like snake skin on one side where you actually had the exposed fibers, and then a resin finish on the other side. And then lastly, our largest specimen untabbed at 25 by 3 millimeters with a resin finish on both sides. Some testing considerations that you want to take into your lab, the following practices: 70% jaw face engagement. You want to have the flat of your tab fully engaged in the grips and have at least 70% of the grips or the jaw faces holding the tab. Not doing this actually risks jaw face pivot at the bottom of the jaw faces, which can risk having your specimen pull out of the grips before even the end of test is done. Next thing that we like to use pretty often when we're doing composites testing or even metals testing is specimen alignment stops. So these stops on the upper and lower jaw faces ensure vertical alignment and repeatable placements every time. And honestly, it just makes it way easier to load into the grips if you're having to hold the specimen in one hand and then close the grips with your other hand. So speeds up testing and make sure that we're vertically aligned properly. Next, at least with our tabbed specimen, ideally you want 100% of your tab engaged with the jaw faces to prevent any kind of premature tab breaks. With the specimens I had and the equipment I was using, I wasn't able to get full engagement, but I did with what I could. And this was kind of a worst case picture. I got better engagement with some other photos. And then lastly, scoring of a specimen. If you are using a contacting extensometer, it's undesirable if that installation pre-damages the surface. Now, this is a plastic dog bone. Typically, we see this happening in softer materials such as plastics, elastomers. And I didn't happen to have any issues with this during my testing as my specimens were robust enough, but you just want to be aware if you have like a softer material or maybe like a ceramic type of composite, you don't want to pre-damage the specimen before you've even started testing. So considerations for ASTM D3039. And I'll have you click for me, Stefan. Thank you. For the class of extensometer, it requires E83 class B1 at least. And if you have a good memory, you remember that clip-ons, we said that they're guaranteed to meet ASTM class B2. When you're getting your clip-ons calibrated, you do have a better chance of reaching class B1 if you have a larger gauge length and low travel. So I used a 2-inch 10% elongation clip-on, not verified, but that's okay. But if we were to have this verified by a service engineer, you have a better chance of getting it classified as B1. So again, if you are using a clip-on, you want large gauge length, low elongation. That gauge length requirement from the standard, you can do from 10 millimeters to 50 millimeters or 1/2 inch to 2 inches. Calculations that care about the strain are your chord modulus or your modulus of the elasticity, your ultimate tensile strain, and then Poisson's ratio. And we only did axial testing with our extensometers, so we're not actually going to report out today on any kind of Poisson's ratio. And then lastly, just some highlights for what kind of specimens you can use in D3039. Tabs are not required. The thickness is as needed, the width is as needed, and really you just need constant rectangular cross-section. So we can see the setup of our 3 specimens at the beginning of the test. I did not have any issues with the clip-on maintaining contact or maintaining that support with any of the specimens that I had, even though they did have varying surface finishes. So if we go to the next slide, we can see what happened at the end of test. And there's actually a video on the left. There you go. So that was a pretty explosive break that we experienced. And I don't know, Stefan, maybe you want to play that again. It's kind of fun to watch. But so the tab specimens were the ones that I actually tested with first. And I experienced those high explosive breaks. And even though my clip-on fell and it fell onto the base of my frame, there were no visual indications of it being damaged, and I was able to use it for the rest of my testing without any problem. Now, something that customers do, they either attach like some kind of cord, or they even use the cabling that comes off of the extensometer, and they actually attach it to like a magnet or some kind of holder on the column cover of the frame. So if you do have explosive failures, that cord will catch the extensometer before it falls and hits the ground. For my second specimen, can you go back? Thank you. For my second specimen, it was a high impact break. Broke just outside of the jaw faces, and thankfully my grips caught my extensometer before it completely fell. And then my last one, my largest tab specimen, did have a break just outside of the jaw face, and was also a high force break, and we were able to maintain contact throughout the entirety of the test. So here are the results of my specimen number 1, that tabbed specimen. First thing that we notice is, so that clip-on remained on during the test, during break. So I actually ended up having negative strain. And the way that Blue Hill calculated my force strain, it actually called out my ultimate tensile strain as 0.178%, just above 25 kilonewtons. And this is incorrect. That's not my ultimate tensile strain. So really, with this kind of test, I probably want to remove the clip-on at around 0.5% of strain, and then just let crosshead displacement take over. And crosshead displacement is absolutely acceptable in terms of end of test criteria, and we'd be able to have the correct ultimate tensile strain with the correct force. Now, my blue line is my chord modulus, or that modulus of elasticity. And the way that the standard dictates it is that it's the slope of the curve from 1,000 to 3,000 microstrain. So that is right at the beginning of my test. So again, because that's like my critical modulus that's being calculated, and we're looking good up until about 1%, which is where we can start to see some of those micro cracks, it's definitely acceptable for me to have removed the extensometer earlier within the test and let that crosshead displacement take over. Next, so my smaller untabbed specimen, this line looks really great. It's really smooth. So this is like an ideal case of using the clip-on. I don't really see many micro cracks. It was able to remain on during the entirety of test. So we tested up to about just above 25 kilonewtons at 1.29% ultimate tensile strain and a chord modulus of 61.4 gigapascals. And then lastly, that largest specimen, which broke just above 60 kilonewtons, we have a little bit of negative strain occurring because of like how high of a break, high impact of a break that was. So it's a little risky that I left it on till the end of break, but I did capture the correct ultimate tensile strain that aligns with my my max force. So this is another instance where I could probably remove it earlier in the test and let that crosshead displacement take over. And then our chord modulus for this one looks good at 66.3 gigapascals. So to summarize the clip-on for pros, it did stay on through break, except in that one case of explosion. I don't think much is going to hold on to that. It had great smooth stress strain curves until those micro cracks and breaks began, and it's very quick to install. Some cons are that messy grafts when left on through failure for at least my first and third specimen. It did pull the incorrect ultimate tensile strain when left on through that explosive failure. And then I didn't always have consistent gauge placement where my gauge length was correct, but the location that I placed the extensometer was a little low, sometimes a little high. So that's just something that comes with practice. I'm not doing this every day. But once you get the hang of it, people are very comfortable and it's very simple to attach it to the specimen. Next, the AVE. So what I'm showing here is my 50 millimeter gauge length that I marked with a white paint pen across all 3 of my specimens. And even though they had different surfaces, I didn't have any issues using that white paint pen to mark my gauge length onto the specimen. And I used a stencil that allowed me to place it in the proper area. For the end of test, again, my first tab specimen completely exploded. So we could see the leftover tabs within the jaw faces. My second specimen, the smaller untabbed one, had similar breaks as the one before, just outside of the jaw faces. And then my last one, it's a little hard to see, but it actually broke in the same location as it did with my clip-on test. So looking at the results for specimen 1, you can already see it's an immediate difference because the AVE was able to maintain tracking of the dots throughout the entirety of the test. And you'll see within that line, there's little like wavy bits. The AVE is extremely accurate. It's accurate down to a micron. So it's capturing everything that's happening within your test. But really what we like here is this nice, we really like this nice straight line showing a nice rise over run. We get an ultimate tensile strain of 1.32%, which is more correct than what we were showing with the clip-on, and a chord modulus of 67.3 gigapascals. Next, we have that untabbed specimen. Again, looks good, nice rise over run, little more wiggly, but absolutely okay. We're still capturing our ultimate tensile strain at 1.38% and capturing that chord modulus at 63.2 gigapascals. And then lastly, we have our largest specimen with the ultimate tensile strain of 1.34% and that chord modulus of 58.1 gigapascals. So for the AVE pros, no contact means absolutely no influence on the test. We automatically read the gauge length. I could have done multiple gauges. I just did 50 millimeters. And then it was able to track the dots through the entirety of the test. Cons is that I did have to manually mark the dots, so that is a little bit of time. Your paint might not work on all of your surfaces. As I said, I was fine with the stuff that I had. And then lastly, accuracy requirements for Poisson's ratio are not met for the standard. And that is to be said, but what's also to be said is that labs still do axial and transverse measurements with the AVE as a comparison. It's not going to be accurate enough to meet the standard, but you still absolutely get usable results. And then I just want to go back real quick for the paint. All you want to do is you just want to make sure that you have some sort of contrast. So I used white paint. You might need to use black paint. But if your surface is not actually taking that paint and it's not staying on, you might have to get creative and use stickers, or you could draw lines on your specimens. But for the most part, paint pens and dots should work okay. So comparing all of these, looking at my force at max load for specimen 1, that looks great. I'm really happy with that. My force at max load for number 2 also looks great. I'm really happy with that. For my specimen 3, it is a little bit off. I'm going to chalk that up to operator error. Composites, as we've said, are influenced by vertical alignment. I could have aligned it wrong. I could have changed my clamping pressure. You're going to have some variables in there that changes that. But What we care about right now are the ultimate tensile strain. For specimen 1, I pointed out that 0.178% is probably wrong. So it's very likely closer to that 1.33%. For specimen 2, those percentages look pretty good in terms of like being close to one another. I'm sure if our equipment was verified, those would be even closer. And specimen 3 is awesome. Only 0.1% off. That's what I want to see. Now my chord modulus for specimen 1, it actually came out lower in my AVE2 by about 5 gigapascals. For specimen 2, it came about 2 gigapascals lower with the clip-on. And then for specimen 3, it actually came about 8 gigapascals higher with the clip-on as compared to the AVE. And Stefan, if you click real quick, why is there such a difference in my chord modulus? And I'll explain why. So I didn't bring this up at the beginning, but ASTM D3039 warns of system alignment. So any kind of excessive bending will cause premature failure, as well as highly inaccurate modulus of elasticity determinations. When I tested my specimens, I set my preload to only 10 newtons, and they broke at 26,000 newtons and 66,000 newtons. This preload was insufficient, which meant that I had some kind of bending in my specimen, and that my excess z-axis was affecting my AVE2 reading. So the AVE2 is not only very accurate in the X and Y in the axial and transverse directions, but also in the direction coming in and out of the lens of the camera. So Stefan, if you could hit a couple times, thank you. So again, preload for my AVE2 specimens was insufficient, and we can see this in my graph on the right where I've zoomed in at 1,000 and 3,000 microstrain. So what we want to do here is we want to have a sufficient preload of around 1% of yield. So my preload should have been at like 260 newtons and 660 newtons, and that would have helped with removing my slack. And also we want to make sure we're testing with calibrated equipment. We're not testing with equipment that's been verified by a field service engineer, but you do want to make sure that your lab is staying up to date on your calibrations and certifications. And if we click one more time, we'll see a comparison of the clip-on. So that clip-on, because it's actually making contact with our specimen, it does not have that z-axis error, but you still absolutely want to make sure that you have that sufficient preload of around 1% of yield and that you're testing calibrated equipment so your lab is having the best chance to capture the best data.
Thank you, Ashley. Okay, now I would like to show you some of the compression testing that we've done for in preparation for this webinar. So the test method that I ran here is ASTM D6641, which seems to be one of the most popular composite compression testing standards from what we can tell here at Instron at least. This test method uses a combined loading approach, and that means that the forces are being introduced into the specimen via shear loading and also via end loading at the same time. You can see my load string set up here on the left. It's a 100 kilonewton testing machine, same one that Ashley was using for the tension testing from our 6800 series. And it's equipped with those same hydraulic wedge grips, but in this case now I am piggybacking fixed compression platens on those hydraulic wedge grips, and then you can see the ASTM D6641 fixture in between those fixed platens. The testing standard actually recommends using fixed platens opposed to using a circle on top, which is still allowed in the standard, but the standard itself is recommending fixed platens. Now, piggybacking, it's a great option to do on hydraulic wedge grips, especially if we go into grips that are much higher in capacity, 300 kilonewton, for example. There's a version of these same grips, 300 kilonewton, that we offer. You don't want to remove those grips, because if you do need to comply to the NetCap alignment requirements on your testing machines, you would invalid your load string alignment verification. So you don't want to remove those grips. And also, usually these grips are pretty heavy. These here you can still install by hand, but if we're going up in capacity, it's not really possible to move those, and those grips by hand. You'll need some equipment. So it's also a nice convenience feature. Now, this particular fixture for the testing I used here was sourced. We sourced this one from the company Wyoming Test Fixtures, which you can see here on the photo. And the specimen is installed in the fixture here. And you can see this testing method is running with a unsupported gauge section, as opposed, for example, to the D695 testing standard. It's only a 13 millimeter long gauge section here between the fixtures, so it is really not possible to install any like common extensometers between there to measure the strain. So you need to use some other kind of transducers in the form of strain gauge, which I will show you as well, but I first want to look at a complete test here. So this is the specimen zoomed in now before the test, and then this is after the test when the specimen failed. So you can see here it failed in the gauge section, and we have a video of the test. And in the beginning, the video is sped up, and you'll actually see the fixture moving down. So all of that compliance within the fixture building up. So the fixture actually moves. And then right before the specimen fails, we slowed down the video so you can see the failure, which should be occurring now. There you go. That's how that looks when you run a ASTM D6641 test. It's very important for a successful test, or it's actually required in the testing standard, that the specimen ends do not crush when the specimen fails. This could indicate that the specimen preparation was improper, and it's very important that the ends of the specimen are machined flat and parallel to each other, and they need to be as perpendicular to the loading axis as possible, really. And you can see here, this is one side of the specimen after the test. The ends did not crush, and then this is the other end where it also didn't crush. On this picture now, you can see the fixture taking apart after the test. So the upper and lower part taken apart with the specimen still in place. And then I took the specimen out, and I wanted to give you a nice close-up picture of the failure location here. So right where the tabs are ending within the free gauge section there. And you can also see here the fixture basically making contact, gripping into those tabs. And that's certainly a lot of that compliance that we've seen in the video when the fixture is actually moving down, loading the specimen. The specimen failed around 45 kilonewtons. It's a unidirectional material. Now I want to show you the same test, but with a specimen with two bonded strain gauges. You can see the specimen that I've used here. It's the same kind of specimen, so it's the same batch that was supplied to us. It's also a unidirectional specimen. And you can see here the bonded strain gauges. So we outsourced this to get strain gauges bonded to the specimen. You can see the strain gauge part number down here, and it's a 350 ohm resistance, which is actually recommended in multiple testing standards. So if you're wondering if you should use 120 or 350 ohm, which seem to be like kind of the most popular versions out there, 350 ohm I have seen being recommended in the testing standards. And here's a nice close-up picture of the strain gauge bonded to the specimen, and you can see the cables here coming from the underside where the other strain gauge is bonded to the specimen. This is kind of also going over how you actually load this, because usually people only see the fixtures, but you don't really see how to put a specimen in. So I figured I'll show you that. You need to be really careful now if you're doing this with a strain gauged specimen. It is definitely possible to damage that. I would always recommend for anybody who's not familiar with this process, hasn't done that yet, to just do it with a non-strain gauged specimen first. And then just to kind of get a feel for it. The fixture is quite heavy. I mean, this is all solid steel. So be careful when you're doing this with a strain gauge specimen. We don't want to get any damage there to the cabling or to the strain gauge itself. So this is how it looks when you start out putting the specimen in the lower part of the fixture with the alignment rods pointing upwards. You got to make sure that you lead your cables out, and make sure that the specimen also fits into the fixture, right? So 140 millimeters length, I think, is the minimum. You could maybe get away with a little bit less, but that's definitely the recommendation within the testing standard. And then you put the upper half on there, and you need to torque these screws here on the side to bring in the sufficient shear loading into your specimen. So you need to make sure that the ends are flush here for the end loading part, right? So you're going to have the specimen here in the first part sit down on the flat surface, and then you need to make sure on the top when you flip it all around and you kind of like put this part into the other one, so that you again get that nice flush bottom where the specimen and the fixture are nice and even. And then you need to make sure that you use the right torque, which again is recommended in the standard. For the first test that I ran to failure, I did use the recommendation in the standard. I think it was 3 Newton meters, between 2.5 and 3 Newton meters, which worked out perfectly as you've seen in my test. So I got the right failure mode and I did not get any end crushing. So that is where you would want to make adjustments if you don't get the right failure modes or your ends crush. And then this is a close-up on both sides of the specimen here with the strain gauges and the cables coming out. And then I place the fixture like that in between the platens, and then you got the cables here leading into our conditioning electronics as we've showed earlier in the presentation. So these need to match the strain gauges that you're using on your specimen. So these are also configured for a 350 ohm quarter bridge setup. And then I took this specimen up to 30 kilonewtons. Again, this is a unidirectional material. It's extremely stiff and therefore also shows very low strain readings. I was actually surprised how low those were, to be honest. I was hoping to be able to show you a little bit more. So maybe taking this all the way through failure would see maybe a little bit more. But yeah, then you get the strain readings of both extensometers, which you could also plot, and you can already see here. So we are really in the 1 microstrain area here. So I had to change the units to microstrain to even be able to display them. And then you can average those two, the results from that. And you can also make an averaged graph, which is the one that we're showing here. So you can look at them individual, or then you can use the averaged one in the middle. So very, very low strain for these unidirectional materials, which is, also kind of like that is one of those characteristics of composites, right? Very stiff materials. And if you ever, this is just something interesting I thought I'd share. So you see the traditional fixture here on the right. There's also custom versions of this, so also supplied by Wyoming Test Fixtures here, where you could use some kind of video laser or DIC. Okay, now I would like to show you some DIC examples. We'll try to make a quick poll here. Are you currently using DIC, digital image correlation software, in your lab? So if we could make a quick poll on that. And yeah, in the interest of time, I'll probably try to go over the presentation and then check back in on the poll in like a minute or so. So just a couple interesting ones that we thought we'll show you. So we have an open hole tensile test here. So you have the open hole specimen, and you can see that random speckle pattern that you need to apply to your specimen. One technique to do this, there's many different ways, all kinds of ways people do this. What I can recommend is just taking a toothbrush with some white paint. You put the white paint on a toothbrush, and then you just kind of flick the toothbrush to kind of get the paint flying onto your specimen. It needs to be random, which is, kind of a fun challenge. And then as the test is running, we're generating those strain fields with all those different pictures in the software. And then this is kind of how that would look like, for example, for this open hole tensile specimen. So you can kind of see here now the software going through all the images. For this one, we had a relatively low capture rate. And then on the right here, you can see the scale for the actual strain. So how are we looking on that poll?
So we got about 28% do not. Oh, do, I'm sorry. 28% do and 73% do not. So about 30,
oh, wow.
70.
Yep. So that's kind of kind of within the expectations. So DIC, it's not a accepted technique in the standards yet, but it's definitely extremely helpful. And you can see the advantage right here, right? I mean, like instead of just having a localized strain measurement, which might not even be the highest strain region with the DIC software, you can see the highest strain regions and then apply strain gauges or extensometers manually. And you can change the size of them, and you can change the location. So you can see here I have one strain gauge simulated here, and then like when you run through that test, this is the curve it generates and tells me, okay, your strain here is around 1.5%. So that is a huge advantage of DIC. We're talking about alignment a lot when we're testing composites, so we thought it's a good idea to give you an example of a purposefully misaligned specimen in your testing. So you can already see it being a little crooked in the pictures. And you can see again here, so generating that strain field basically from the point where strain was actually being put on the specimen. And you can see that those areas here on the top right and on the bottom left are building up. And yeah, towards the end, they're just kind of turning into red, where we're really getting to the 1.6% strain reading. And then at the end, definitely not a good failure here. Broke on both tabs. This is why alignment is just so very important. And then I put a virtual extensometer from the bottom corner here over to here, and then this is that strain reading within that corner. So it's taking that average strain reading over this distance here. And then lastly, I want to show you quickly a mixed mode example. So this is where you can use the AVE2 for your actual strain reading. And if you are interested in the strain fields of the rest of your specimen, you can put that speckle pattern there and then get those strain readings right at the same time while you're getting a verified, or let's say you can use those strain readings here in actual direction with the AVE2, and you still comply to your testing standard, while at the same time getting interesting information on your specimen, like on the strain fields of your specimens that are happening outside of that gauge section, right? So you can kind of, with this one, I think this is the exact same tapped specimen that Ashley was using. And you've kind of seen that every time that specimen kind of failed at the taps, right? So now you can kind of see what was actually happening there, right? So we're taking that strain reading here, and if you were to use a traditional clip-on extensometer or just the AVE with the dots, you would be unaware of actually what is happening here. I think everybody can kind of, imagine that, like, you have the tabs sticking out a little bit too far, and then they're kind of like peeling back, and then it's kind of influencing your specimen. That's kind of what it looks like over here. And another quick thing here that was interesting was that you had actually like the first, like one of the plies of the specimen seems to have delaminated here towards the end of the test and actually came off. And then you can see the software is not able anymore to generate the strain field within that area. So depending on your failure mode, that might be something that you need to keep in mind when you're running DIC on your specimens in your lab. Okay, so with that, I don't think we have too much time anymore for questions, but yeah, if we can take one or two quickly, then we'll try to answer them.
All right, thank you so much. That's a great presentation. So like you said, we've got a few minutes here. We'll grab a few questions. I've got a few submitted already, so we'll start there. First is a clarification question. Can the axial clip-on extensometer test up to 200 degrees Celsius, or can you clarify the temperature range on that?
Yeah, so you clip-on extensometers, 200 degrees is kind of like, I think for the standard clip-on extensometers, the upper range, at least the ones that we are offering. Then there's always special versions out there, right? So it might be I think they're called capacitor extensometers. Those are usually able to go at much higher temperatures. So there's always some options. We just kind of focused on the the majority of or the more simple also versions out there that we have on hand here. But there's certainly special versions that use different techniques that can go to higher temperatures.
Okay. What are the limitations on usage of AVE2 in composite tests? For example, could you use it for compression tests?
Yeah, so compression testing, I mean, you could try, I guess. You really need to make sure that you can see that you're able to see the flat side of the specimen. That's really where it gets tricky. The other thing is like there's a lot of fixturing involved usually, so the view is not really it's not really going to allow you to view that flat side of the specimen. And the other issue there is if you do need to follow the testing standard, there is really no other option than using strain gauges in a lot of cases. So you need to prove, for example, the ASTM 6641, even if you were to use the modified fixture that I've shown there quickly on the picture from the Wyoming Testing Fixture Company. Even if you were using one of those, you wouldn't be following the testing standards in terms of proving that your bending was less than 10%. That is one requirement in the standard, which you need to prove with those two bonded strain gauges, as I've shown in my pictures there from the second test. So you can't really do that if you're using a video extensometer. So fixturing is an issue, and the other issue is really being in accordance with the standard. If that is more like a R&D kind of situation, then I think probably using DIC in that situation is probably like getting one of those modified fixtures and putting a random speckle pattern on there and then making a full field, a full strain field is probably something that I would personally be really interested in.
Okay. So we're reaching kind of the end of time here, but we'll grab one more quick question. Last one. How are clip-on extensometers detached when running a test?
Yeah, so if the question is kind of in regards to what Ashley was mentioning earlier, so you can pause the test, or there's so this is pretty common also for metals testing. So our software supports that, where within the software you can kind of program it so that at a certain point, so for example for metals testing that would be after the yield region, you can kind of have the test pause, or you have to, there's all different kind of options, but you can have the test pause to remove the extensometer. So the test will automatically do that and then throw up a message on the screen for the operator to say, okay, it's time to remove that extensometer from the specimen, and then the operator carefully will do that, and then you can confirm on the software screen, and then the test will continue all the way through failure. So that would be one way of capturing that, like whatever your requirement is, right? Like whatever, like if you need to test it all the way through failure, you kind of have to leave it on, right? But if you're just trying to capture that first initial region to determine your modulus, for example, then that would be something that you need to kind of know, when does this specimen fail, right? That's kind of like you're only like, you probably want to test one or two before to get a good idea. Okay, these fail at like 40, 50, 80, 100, whatever kilonewtons, and then you put your extensometer removal point accordingly.
All right, thanks so much. So we have come to the end of the webinar now. There are a few questions that were submitted that we didn't have time to address, so those will be forwarded to Instron. You'll have a chance to respond later if you like. And we will be sending a recording of the webinar to all attendees afterwards, so look out for that in an email. Stefan and Ashley, thank you again for this presentation. We really appreciate it.
Thank you.
Thank you.
And thanks for attendees for joining us today. Have a good day, everyone.